I think the participants has stabilized at a certain number, so we can start maybe.
That's okay. I think, yeah, that's fine. So, yeah, I think I'll just introduce myself first, just to welcome you all here before we can start our workshop. So, yeah, so I think I'll start with my introduction. I don't have a specific slide where I have myself introduced, so I'll just do it verbally. So, my name is Ian Okoth. As you can see on the slides here, I'm serving as the current chair of RASCadia. That is Robotics and Automation Society, IEEE chapter. I'm also a student currently in my 4th year at the Technical University of Kenya. So yeah, I'm currently taking or doing my undergraduate in electrical and electronics engineering. And this is what my passion is, or this is what I love to do. So when I was asked to come present in this workshop, I think for me, it's something that I love to do, and I'm willing to spend hours to talk about. So yeah, so I am also glad to see that we're having also a collaboration between Kenya and many other countries. I think it's around 5 countries, which is really good because we are having a diverse set of attendees. So that means that we are diverse. The next time you're going to have maybe a speaker from a different country, and we can learn more from each other that way. Yeah, so also just another side note, if I'm moving a bit fast or slow, you can just inform me, and I'll do my best to go at a rate that is favorable for everyone. Also, lastly, I sent you some documents on the WhatsApp community, the group PCB design community. So I hope all of you have downloaded KiCad. It's not that big. It's about 1.4 GB, if I remember well. Also, I also hope that you also have the files I sent. Those are the files that we're going to use for this workshop. So yeah, I'm glad to see you all here. See 57 people have joined. So that is really good. Yeah, so with that, yeah, I'll not waste any much time. We can just go right into it. So yeah, so the first thing is the topic today is PCB design. And from what I understand, everybody was choosing on what to go, what workshop to go attend. Or maybe I don't know if you're able to choose multiple, but I think on the basis that you chose PCB design means that you know something about it. Doesn't mean that you are a professional or even intermediate, but you know the name, you know that what is a PCB, you know some things. Okay, what's going on? Okay, don't know. Anyway, yeah. So you have some kind of idea, and while I was coming up with these slides, it was a choice because I was thinking, should I go maybe intermediate or beginner level? But I think for most of us, many people are at the beginner stage, and that is why I decided to tune this presentation to go towards the beginner side of things. So I think I've spoken a lot there. Yeah, so I'll start. So the first thing is, if we look at this point here, you see that we are using KiCad. And there's many, I would say, platforms that you can use to design PCBs. There's Altium Designer, there's Eagle, we have Proteus, we have Easy EDA. But the reason why I work with KiCad, many people have different choices. Some are using Altium Designer, some are using Eagle, some are using Easy EDA, and all of them have their advantages. For example, the Easy EDA, it's quite easy to collaborate with someone else. It's like working on the cloud, whereby two people can be working on the same project at the same time. One could be working on one section of the schematic, and another person will be working on the other side of the schematic, and it's all being intertwined. They are able to work on one project as two people. But you find that on KiCad, you cannot do that. Also, if you go to Altium Designer is not free. It's a paid option, and it has more features. There are things that will need to calculate. And on our own, in our case, we won't have the tools to calculate those things. I'll not say what they are because you might not understand. Maybe trace width and differential pairs. You might find that the calculation exists on Altium Designer. It is inbuilt on the app, but in KiCad it's not. So you find that every platform has their own advantages. So if I've been giving this the what other platforms are better in, but I've not talked about KiCad. So the reason I'm using KiCad, and the reason many people use KiCad, is number one, it's open source, meaning it's free. That is why I asked you all to go download KiCad. And you find that if I said Altium Designer, then you would have to pay. You will have to pay. Or if maybe you do some sketchy stuff, you can decide to get a cracked version. But you typically have to pay for KiCad. So that is not something that is available to everybody. And especially if you don't know about PCB design, why should you pay upfront? So KiCad is a good option. The second thing is it's the best open source PCB design tool to exist. And there's many companies, very big companies, that use KiCad as their software because it's open source. I can send a file to somebody else somewhere in the world, and they will be able to have KiCad. KiCad is known internationally. So I think, so those are the advantages of KiCad. So let's just go into it. So an introduction, what is a PCB? A PCB stands for a printed circuit board. And for those who are quite new to this, printed circuit boards, if maybe you look at any electronic, there's usually this green board, and that board has a number of components on it. And an example is this here. You can see, you have seen something like this. Your phone has it, the televisions have it, the remote has it. Every device nowadays, they usually have PCBs because we are living in a digital world, and digital means that we're all running on electronics. So that means that we have seen these things. It's something that we have seen, we have interacted with. And you see, the funny thing is people use these devices, but they don't know how they work. For example, you use your remote, the TV remote, every day, and you find that even children are using them, and it's being used by everybody, but people don't understand what is happening on the background. And that shows you that these electronics have been designed very well to the point that they are easy to use. But in the background, complex things are going on. And that is now where we are involved, where I think there's something that Steve Jobs used to say, that a device needs to be really complex so that somebody can find it easy to use. So you find that maybe, for example, your phone is running on incredibly difficult or hard or I'll say complex algorithms, but you are seeing a really good experience, but on the background, what is going on is intense. Or for example, AI, the ChatGPT, Gemini, is incredibly complex algorithms going on in the background. but people are just using it every day without knowing what is going on in the background. And that shows you that complexity results to simplicity, but not always, but I'll explain more on that. Next is the foundation for almost all modern electronics. We have spoken about that. It holds components and connects them with copper traces, replacing a messy tangle of wires. That is something we're going to see. A simple analogy, and here we're using maybe a human body. And you find that the skeleton is basically the structure. It is your structure. And it is what is holding the organs. And the organs are going to be the components that we have, maybe the resistors, maybe the capacitors, and they're being connected through the PCB, the board. And that is a concept that we are going to see well. But if you look at this picture here specifically, or all the pictures, we are seeing here we have a green board, a purple one, here is still green, and you see these components here. These components here are on the board, and the traces are running on the board, the connections. And you're going to see that clearly when we're doing a demo on KiCad. Next is, why do we need PCBs? Why not just, I know not 100% of you, but a big number of you guys have worked with breadboards. And the question is, why not work with breadboards? And I think even before I answer that question, you already know the answer, that a PCB can be very compact. A breadboard cannot, or even, I think the other one is called what? Puffboard or what? I think whatever. But a PCB can be made to be very compact. And the resistors and the capacitors can be really small, to the point that you can have a compact system. And that is clear on your phones. And when you look at the electronics sector at the moment, you're seeing that the phones are becoming thinner and thinner every day. And this is showing an advancement of electronics, because basically the key thing in electronics is to make it as compact as possible. That is why the advancements of electronics resulted into smartwatches. Because previously, for you to get the same power that can run maybe, for example, the Apple Watch, to get the same power, it will have to be a very big PCB, which could not be very realistic to fit on your hand. And this also is also an advancement on the chip side also, because chips have become also smaller and smaller and more powerful. They are smaller and more powerful. But you find it's these advancements that are resulting in more compact devices. And as we go on into the future, the devices are going to be even more compact. I don't know the future for phones or where it's going, but what I know is that things are going to be very compact. So yeah, so the first thing is reliability. No wires, no loose wires to come undone. When you look at a breadboard, for example, we usually use jumper wires. And these jumper wires that we use, we usually connect components. Maybe let's say we're using Arduino, for example. I think Arduino is known by most people. If we're using Arduino, then you find that you're using the jumper wires and connecting them to the sensors. But you find that these connections, number one, they are not as strong as the connections that exist on a PCB, because the PCB is not, what can I say? The PCB, the wire cannot come loose. And I think that's something we're going to show when it can only be seen through KiCad. You cannot explain it easily, but you cannot compare it to a breadboard. That's the first thing. Second thing is repeatability. Every board is manufactured is identical. Another example, for example, if you have maybe a Samsung phone, you find that if you're having the same model, it means that it has the same board inside, meaning that this board was manufactured at scale. It was manufactured at scale. meaning that they were able to replicate the same board multiple times. Even, for example, the television sets, that is the same electronic device, same dimensions, but has been reproduced at a massive scale, to the point that you can now be able to have the same product everywhere. And that is why repeatability is key, because you can now have the same product 100% of the time. Next is the size, can be small and compact. That is something we've been talking about. Cost effective for manufacturing more than one unit. And I think to those who understand PCBs for a bit, or even understand business, you find that the more you order something, let's say, for example, buying, I don't know what, let me give an example with milk, because milk is universal. Buying milk in bulk is cheaper than buying one unit. If you're buying at a massive scale, then the cost reduces as compared to buying one unit. And that's the same economics for PCBs. The more you order, the cheaper it becomes. And I think this is also the reason why, for example, companies like Apple have outsourced their manufacturing to China, because of the scale that they have. They have massive scale, and this scale is what now they use now to make sure that the costs are so low. And also there's many other things at play, but that is also a key component. Next is the PCB design journey. So the question is, now we are moving from what is the process of creating a PCB? What process do we follow? What steps do we follow? And we are going to start here with number one, idea. So we usually have an idea. We maybe want, for example, let's pick maybe a device that we want to manufacture. Let's say we are having a device like, we want a device that you can use in agriculture. And this device, we want to place it in the farm or on the farm. And we want it to be able to be connected to sensors that can measure the parameters of the farm. For example, there are some kind of plants that have specific temperature ranges or humidity ranges. So you find that we can use maybe a device on the farm that can be able to monitor these values. So this device is supposed to maybe monitor temperature, is supposed to monitor humidity, it's supposed to monitor maybe light intensity. It is also supposed to measure maybe soil moisture. It could be many things. And you find that it all starts with the idea first. And the idea is not usually generated randomly. It is usually to fix a specific problem. And for example, it does not make sense, okay, unless it has a purpose, but it does not make sense to just have a device that just monitors these values. Because if maybe, for example, the plant should exist between, the temperature should be between maybe 25 degrees Celsius to maybe 30. And the temperature goes to 35. A monitoring device does not help anything, because it's telling you, yes, that the temperature is not okay, the temperature is high, but what is it doing about it? And that is now where we can have an intelligent device that maybe if you're in a controlled environment, like a greenhouse, then we can now activate maybe fans. The same device can activate a fan that could maybe reduce the temperature, or it could do something to counter that issue. So that is now where we are going into IoT, Internet of Things, where we can be able to make decisions based on data. But that is something that we're going to go through. But it all starts with an idea. You have an idea, this is what we want to achieve. And then now, that is now when we can say, okay, have we looked at other options? Maybe there could be simpler options to that. I don't know. Maybe there could be simpler options. But we go into PCB design, and you see PCB design is custom, meaning that you're building something custom. And before we start even designing a PCB, we need to also ask, does there exist similar PCBs, not PCBs, but similar boards on the market, or boards that can solve the problem even before you go custom? Because custom usually requires a lot of money, especially if you're doing small units. It usually requires a lot of money. So you need to maybe first ask if there is something on the market before you go into trying to design your own custom PCB. So from the idea, now we have idea, something concrete. Now we can now go on to the schematic part. And the schematic part is now whereby we, okay. Oh, I see somebody. Can you hear me well? Just looking
Yes,
at it.
we can hear you well, yeah.
Yes, we can hear you perfect. You're doing a great job. Thank you.
Okay. So now we can now go on to the schematic section. So the schematic section is now whereby we start to now look at, okay, the implementation. Now we have the idea, but now we need the implementation of this idea. And it all starts with the schematic. We start with creating the logic of how things are going to flow. What will this component do? How will it be able to get data? How will it be able to send data? You are now creating the logic of how this PCB will function. And then now we can now go on to the layout side. And these things, you're going to see them clearly on KiCad. The layout side, or the layout section, is now whereby we are arranging our components on the board so that you can have the most optimal size or the most optimal outcome. For example, it does not make sense to place components far apart when they can be close to each other, because it reduces cost. The smaller board is cheaper to produce than a big board. So you find that mostly people usually want to go for compactness because it's cheaper. But also, there's some components that you cannot put close to each other. And you also have to give them some distance. Even, for example, traces. I think some of you know of the communication protocols. I don't know if some of you know I2C or SPI. I'm not sure, but those are IoT concepts. And you find that there's usually maybe, let me give an example. There's usually maybe two wires. One wire is sending data and another wire is receiving. For example, in UART, we are having a receiver wire and a transmitter wire. And usually in PCB design, these two wires cannot be so close to each other because they'll start to interfere with each other. The information will get corrupted. So you have to give them a bit of distance between each other. So even though we are trying to reduce the size, for example, let's have this maybe two wires here. If we are trying to reduce this distance between the two here, this distance cannot go below a certain point. They cannot go below a certain point, because if they come so close to each other, maybe somewhere here, maybe somewhere at the center here, these two wires will start to communicate with each other. And you find that the time you're trying to read the data, it is not clear. It has been corrupted. But that is something I'm also going to show. And also it has some implications with the manufacturers. They usually say that we need the design to be to have certain limits. So we are going to see that. So that's not an issue. Okay, next is the manufacturing and assembly. That is not something I'm going to talk much about at the moment, but you're going to see what I'm talking about. So Yeah, just looking at the comments here, I think I see everybody is okay. Yeah, I'm also seeing text or a message for me to send the PDF. I'm going to send it immediately after this. That's not an issue. Okay.
Thank you.
So I think till this point we're okay. Now we can now go into now the key concepts. There's many. If you were to go into all the key concepts, they could pass maybe 5,000 key concepts. But these are the major ones. Number one, schematic. That is the engineering drawing for your circuit. It's all about logical connections, meaning that we are creating the logic and you will understand what I'm saying. Also, we can also still say that creating or writing the code is also creating logic. And those are basically the same things. Because when you're doing hardware or PCB design, you're basically saying current should flow through this specific path. That is also creating logic because you're saying current should move from this point to this other point here. But also writing firmware, because these PCBs that exist on their own, they don't need any programming. For example, a converter or like something like, yeah, maybe a converter, maybe a device that is being fed maybe 12 volts and it's giving an output of 3.3 volts or 5 volts. You find that there's no code in that system. It's all about basically dissipating the difference as heat. So we are not really writing any code. But now when we now go into IoT, then we have to write code because we're using chips that cannot function without code. But again, those are things that you're going to see well on KiCad. Next is components. The parts here, resistors, capacitors, and chips. They have symbols for the schematic footprints for the PCB layout. So the components. Hello. Okay, I don't know what happened there. Anyway, if you have any question, just send through the chat or you can unmute. Yeah, whatever works for you. Okay, let me continue. Components. We are basically having resistors, capacitors, inductors, all those things, all in the schematic. And now we can now move towards the PCB design where we arrange them in the most optimum way for our application. And then, yeah, the footprint you're going to see. That is not something that is.
Sorry, someone has asked you a question. He
Okay.
said, "What are the things that doesn't need coding?"
Okay, I'll give an example.
Yes.
Okay, I'm trying to find something common that we usually use. Something common. What is common? Because they're DC-DC converters, we are having because DC-DC converters, they basically take in a specific voltage and output a specific voltage. And it's all in the connections. It's all in the resistors. Meaning if you pick a specific set of resistors, it basically just drops the voltage from 12 volts maybe to 5 volts. But there's no code. There's no code being written for this device to drop the voltage. But I think, let me go through these concepts.
Chargers.
Even for example, a good example is the laptop charger, for example. It's basically taking in AC and giving out DC. Yeah, even phone chargers. Yeah, there's many ideas. I was missing this, but there's actually electronics that don't need code. They don't need code. But if we now go into IoT, into those things where we're using maybe chips, that is now where we need code. But there's electronic devices that don't need code. A phone charger is a really good example for this case. Yeah, I hope Akray, it's okay. Yeah, power supply circuits, voltage regulators. This is what I wanted to show here. I wanted to go into to show an image. This is good. Yeah. So, okay, let me continue. If you have any question, I'll see them. Just write on the chat box. PCB layout, the physical implementation of the schematic. I think this is something you're going to see. Traces, the copper wires on the board. Let me show you traces. You see this, I hope you can see, I hope my cursor is a bit visible, or let me use this pen here. These things here, these are traces. These are what are called traces. Typically, if we are using a breadboard, you see, for example, this wire here that is going this way here. This wire could have been a jumper wire. It would have been a jumper wire here. But in this case, we are using a wire that is
printed.
Okay. Hello?
Is it a wire like printed on the
Yeah,
board?
it's exactly. It's a wire, and it is a copper wire. It is a copper wire of a specific thickness that we can use to connect components. So that is why we can be really compact in PCBs as compared to breadboard, because you can see this is a very small wire here. Let me just erase, let me erase this. Okay. So as you can see, even these ones here, these are wires connecting components to another component. Let me see if we have a wire. For example, you can see this trace here is coming from this capacitor and going this way. You see, and it's showing you that it's moving somewhere. It's going somewhere. So I have a question just at this point. And I think I just want to make this a bit interactive. Why? Because this is a trace here. This also a trace. But you find that these ones are thin. These ones are very thin as compared to this here. Who could give a reason why? Why are these? Yeah, I see someone raise their hand. You can just unmute and you can just speak.
It is because of the current that flows into them.
Perfect.
The thicker one holds more current, so that's why.
Exactly, and that is the reason. That is the main reason why, and that comes down to the basics of, for example, to those who understand about doing wiring in the houses. You find that there are wires that you can use for maybe the lighting, but that is not the same wire you can use on the cooker. The cooker draws a lot of current, and if you try and use the same wire for lighting to basically wire the cooker, you're going to burn your house, because what will happen is that wire will not be able to take the current, and that is going to destroy. It is going to destroy that wire. So yeah, I think I see you guys understand the concepts, and that is really good. That is really good because it isn't the process. So I see also another question here. Could a computer bus system be like this on a motherboard? Yeah, totally. That is something that is possible. Although, okay, I just took a picture of this because it showed the traces very well. I don't know if this is a motherboard, but what I know is that motherboards usually have the components are usually very close to each other. They're usually very close to each other, and then the traces are usually. Hello, you can just speak. Okay. If you have any question, just write on the chat box, or you can just speak. Yeah. So I think we can continue. So a note down here is that we are going to focus on the schematic and PCB layout today. So we are going to focus on these two things, schematic and PCB layout. There's maybe if we have another session, we can now focus on manufacturing and assembly. And because I'm not going to dwell much into it, I'll just mention why it is important. So okay, I'll just give you a bit of background of myself before I even go into this, so that I humanize the concepts. I started doing PCB designs. Okay, I started with IoT, Internet of Things. So I think most of you know Arduino. So I used to do projects using Arduino to Arduino, Raspberry Pi, mostly those two. And the Raspberry Pi, actually, I joined, or I started IoT. There was a workshop by Raspberry Pi in Kenya, and they were giving free boards and free sensors. And I think I was lucky to have been selected to participate. So I went there, I learned about IoT, and I was given the board, and that was the platform for me to get into IoT. And it was a Raspberry Pi Pico, to those who know it. We were even going to go through the schematic of Raspberry Pi Pico. So after that is when I started doing a number of projects, participating in competitions. And then from that point is whereby I decided to now go into PCB design. Because for me, I feel like, for example, when you're using Raspberry Pi, for example, you're using a finished product, but there's somebody that designed it. And you find that maybe when you're using the Raspberry Pi, usually maybe sometimes you use maximum of, it has a number of pins. I don't know, it's 30 or something, but we're using maybe 8 pins. Then why not design a board that only has 8 pins if you are creating something that is not going to be changed? So for me, I felt like it's better for me to learn PCB design, because I could create custom designs for my own uses. So that is something that I have been doing. I see a hand raised. You can just unmute and speak.
I just want to ask about the manufacturing of these PCBs. Like, do you contact a verified manufacturer or a company or what?
Exactly. So I'm getting there. So when I went into the PCBs, I eventually got to a point where I wanted to now design my own boards and sell them locally. And the reason I'm giving this backstory is because it's all leading to manufacturing and assembly. Now, we are at the manufacturing stage. I've designed the schematic, the PCB layout. Now, the thing is, I now have everything. I have the schematic, I have the PCB. How do I manufacture the board? So what we usually do is, there's 2 options for us in Kenya. I don't know in other countries, but for us in Kenya, we have 2 options. Number 1, we have a local producer, somebody who has the machines to create the PCBs or to manufacture them. So you usually take to them the GABA files. I'll show you what GABA files are, and they'll manufacture those PCBs for you. And they're also quite good. They are more expensive, but they're quite good, because if your PCB has an issue, they'll not print that PCB as is. They'll tell you, okay, this PCB, this is going to be an issue. They tell you, do this, go and rectify this. So they are more of a kind of a partner. They look like a partner, because they tell you, this is okay, this is not okay, and they're not going to print a defective board. But the second option, I even see some of you know them. The second option is now China. And China has both a company called JLC PCB or another company called PCBWay. There's more companies, but these are the ones that are known, JLC PCB or PCBWay. So these two companies, they have the capability to produce these boards at a very cheap price. Their cost is so low because they're basically the manufacturers of the world. Most of the manufacturing they do. So you find that because they're operating on scale, their prices can be very cheap. And also, so you find that locally, you can take the GABA files to the company, and maybe in about 1 day or 2 days, you have your board. But for them, you have to ship to China, wait, and then it's back. So it depends. It depends with what you want to do. It could be, if you're having something that has to be produced within a short time frame, then for us, we could just go local. But even, okay, still, the worst thing is you still have to import also the components because they don't have the components. And it does not make sense from a business perspective for you to keep stock of the components because people have very custom designs. You may stock this component and someone uses another one and you end up making losses. So you find that the best way is to just import from China. So it will still take the same time. It will still take the same time. So that is why usually cheaper, I mean, China is usually the best option. China is usually the go-to option, JLC, PCB, or PCBWay. Those are the best options. You send them the GABA files. If you want them also to assemble the board to assemble, meaning to have the components, to place the components for you, then what you can do is to send them the bill of materials, which I'm also going to show, and they will be able to assemble it for you, but at a higher cost. And also, lastly is, yeah, I think I'll keep on mentioning these things as I go forward, but that is what manufacturing is about. So we just mentioned here JLC PCBWay, JLC PCB, and then we have PCBWay. You can now go to their sites, look at what they offer, and you'll find that they're surprisingly similar. And they basically do the same thing. They do the same thing. So yeah, yeah, so we can continue. I hope I forgot the name of the person who asked the question about manufacturing, but I hope you get a better understanding of how manufacturing is.
Yeah, thanks.
Okay, thanks. Okay, let's continue. So we now go to vias. Vias, I'll explain. That is not something that you can understand here. But if you look closely, let me just get the pen here. If you look closely at these things here, I want you to look at these things here. They look like holes.
Yes.
Yeah, they look like some small holes. Those are called vias. Yeah, these are called vias. And you will see from the presentation or from KiCad that there's usually, when you're designing PCBs, it has layers, meaning that we can have a 2-layer board, we can have 4-layer board, we can have a 6-layer board, depending on the use case. But you find that if you also have some components at the bottom, or okay, I think vias are better explained through using the KiCad platform. So, but still, these are called vias. Just know that these are holes, that help you move from the top layer to a different layer. They help you move from the top layer or from one layer to another. Let me just say that. I see even somebody.
Sorry, I have a question. So
Okay.
they connect the layers. You
Exactly.
mean that?
Yes.
Okay.
Yeah. And you're going to see it practically, because I think saying just layers, there's somebody who doesn't even understand what a layer is. So you find that sometimes they may not understand what we're talking about, but it's okay. Again, as I said, it's a beginner-oriented presentation. So yeah. So I think till that
Could you
point,
please repeat what's the purpose of the vias?
the vias is to connect not two layers, but to connect multiple layers. You can move from one layer to another. And let me give an example. Where is it? Let me just draw a diagram here. Assume that we are having a two-layer.
One question.
Yeah.
Is there a limit for the layers?
Okay. I never did research on that, because for me, I usually create 2, 4, and 6 layer boards. That's what I've worked with. But I see somebody on the comments here saying up to 16 layer, because I've heard of also 16 layer boards. But it's very rare, because you can achieve a lot with a 6-layer board. If things are really tough, then you can just go for a 6-layer board. 16 layer, you find maybe companies like SpaceX are using them, but not. It's quite complex.
What about PC motherboard?
PC motherboards, I don't really know. But if I'm to make an assumption, I think 6-layer board is okay. But let me explain what these layers are for, and then you're going to understand why people choose these different layers. And I'll give an example of how somebody can decide to choose a 16-layer board. So I think that's a really good question, because it's something that maybe I could have overlooked. So number one, let's have this board here. I hope you can see my screen. You can see the 2 lines I've drawn.
Yes.
Okay, perfect. So this is a 2-layer board. This is layer number 1 on top here. Okay, let me draw it in a different place, because here it's obstructing my view. Let me draw it. Let me see. Yeah, let me draw it somewhere. Okay, sorry. Where can I draw it? Let me draw it here. We have this and this. So this is layer number 1. This is layer number 2. Okay. So what usually happens, this is not, okay, I'll explain more about the layers. We have some components at the top here. Maybe a capacitor. Maybe a capacitor here. Maybe a resistor here. Don't know. Maybe these things are present. So sometimes you find that when you're routing the board, okay, let me just delete that. Okay. So sometimes you find that when you're routing the board, for example, where is it? We're routing this board here. This is the top side of it. Okay. And assume that we are also having the bottom section here. So sometimes you may route these wires, and the wires are so intertwined to a point that you find that it's like they are blocking each other to some extent, that these wires, you cannot route them optimally. And you're going to see them, you're going to see this on KiCad, because here it's difficult to draw. But sometimes you may have like a very complex PCB, not even complex, just having more components. And you find that the wires cannot just route end to end. And usually what you need to do is to create a via somewhere here. that will move you from the top layer to the bottom layer here. And then now you can route at the bottom. And then once you are past, maybe there's another wire passing here, and this wire was moving this way, but it cannot pass through this point. So what you do is go down, move at the bottom, and then go back up and continue routing this way. I don't know if this illustrates it correctly, but I hope it does. But you're going to see more through KiCad. But you can see that we are having a wire going this way. But also at the same time, we are also having a trace also, another trace crossing it like this. So you cannot pass, you cannot route on top of another trace. So to evade this wire here, you go downwards, route at the bottom, and then go back up, and then continue routing. So basically, you have avoided this wire. I think this concept is going to be really important when you're looking at the PCB. I hope you're able to understand it, or the concept, because it's going to be very important. But
what I'm understanding from this, that basically...
Oh, you get it?
I get it, but let me just confirm that.
Great. Yeah, you're going to understand better. Yeah.
You just put the basic components on top in the top layer, and you can deal with a group of these basic components as one part, then go to the next layer, connect with them with each other. Am I saying this right?
Yeah. So yeah,
I have a question.
That's okay. Continue.
Why vias have many different sizes?
Perfect. That's another good question. Okay, so the vias again have current carrying capacity, because I think you're asking a really good question. Because if you look at this one here and at this one's here, this one is bigger than this, and the vias usually have a current carrying capacity. And you find that the bigger the size, the more current it can hold. And also sometimes it depends. And I'm going to show you on the KiCad design that we usually have also bigger ones or custom sizes depending on what the manufacturer says. You cannot just pick any via on your own. You have to go look at what the manufacturer is saying, and then you can now choose. And I'm going to show you what to choose from. But that's a good question. This one here is bigger than this here. I think it's about current, and that is what I know. Okay. Okay, I think I've spent too much time on this section, but I'm glad that you guys are understanding the concept of a via. A via is very important. I'm glad you're able to understand it. So I think till that point we're okay. Now, the next step, we are now going into KiCad. We want to have a demo of KiCad. So yeah, so the time now is 10. Time now is 10. So what you can do is we can have a short break of about 6 minutes or 5 minutes or even 10 minutes for you to have a bit of a break and for you to open KiCad, and then yeah, at 10:10 we're going to again start.
Okay.
The break is 1 hour.
No,
1 hour break.
No, not 1 hour.
No, 10 minutes.
10 minutes.
10 minutes.
10 minutes.
Yeah.
Oh, okay.
I want to ask about the KiCad license for academic purposes.
Does KiCad have licenses? I didn't know about that.
There are academic licenses, but you know, I tried to download it, but it says just for 6 months. I don't know if that's right.
I have just downloaded, and he didn't ask me for a key or a license.
Yeah, it's open source. I don't know.
Okay, I'll try again.
Okay. Okay. If you have any questions, just reach out to me on my WhatsApp, and I'll help you. I'll help you figure out.
I think
see
I
somebody.
just
Okay.
I think I've just gone for the wrong one. I went for the Cadence one. I think there are more than one company that has this software.
Okay. Okay. I also see somebody asking, these are two questions. Which version of KiCad are we going to use? KiCad 9.0, because initially I was even using KiCad 8.0, but a few months ago, I think 1 or 2 months ago, KiCad released the KiCad 9.0. So you find that if you try and open a KiCad 8.0 file with 9.0, initially, when I downloaded it, sometimes the KiCad 8.0 was losing some of the contents. So I just prefer that you just download KiCad 9.0, the latest one, just the latest one. The program name is KiCad. That is the name. Yeah, 9.0, 3 to 4 months ago. Yeah, I remember downloading it again. Okay, then I see another question. Will you finish setting up the app with us? Yeah, that's okay. Depends where you are. What position are you in? What stage? What stage are you in? Or what stage are you at? What's the best? What I don't know. Anyway, so let me just share my screen on KiCad. Okay, are you able to see my screen?
Yes.
Yes.
Okay, great. So yeah, so let's wait till then you're okay. If that's the stage that you're at, you're okay. That's okay. You don't need to have these files here. These files, okay, you need to access them through the group that is through the link, not link, but there's a zip file I sent in the community. I think you can take a look at them. I'll just tell you what to download, so that's not an issue. Let me just even look at them at the moment. So so if you open the zip files, if you open not the zip file, but the zip file one, you find that there's two projects. We are seeing dark keyboard ESP32, something like that. And then we're having project Pico main. Okay.
Yes.
So I'll just tell you which one to open, but you're going to open both. But at the moment, you don't need to open any of them. You're just okay, because we want to first go through the user interface, and then from that point we can now go into now seeing the projects. So don't worry about that. Okay. I see the time is up, so I think we can continue. Yeah, so I hope all of you are seeing a screen like this. You're able to see a screen like this. I don't know. Maybe you can see through the chat box, maybe thumbs up or something. I don't know. But I'll just like to see the number of people that are able to see such a screen. I only see one person. Where are the rest? Where are the rest of you guys at? Are you stuck? Okay, don't know. That's okay. No files on the left is okay. That's not an issue. That is not an issue. Yes, Islam. Or Islam. Don't know. Islam. Okay. Okay, I see. Okay. Let me continue. So what you're seeing here is the screen for KiCad. And we are seeing a number of things here. Just ignore this section. Ignore this section here. You don't need to know much about that at the moment. So we're just going to go through the interface of KiCad. And you're going to start with, okay, you don't need to see a lot of things here. The most important things are here. And the first thing here, we're seeing the schematic editor. We are seeing symbol editor, we're seeing PCB editor, footprint editor, GABA viewer, all these things. But as I said, today we are going to focus on only two things, schematic, PCB. So those are the things that you need to have more emphasis on. That's what you need to see. So schematic editor and PCB editor. Those are the two things that you need to see. So I'll stop sharing the screen and go to the schematic. So what we'll do, the next action is press on the schematic editor. Press on that part. Let me just point it so that here, press here. Okay. And you should see a screen looking like this. You don't need to have these components. It will just be blank for you. It will be blank, but you don't need to see these components. I hope you are at that point.
Sorry, can you repeat what you just did?
Okay, so let me just stop sharing the screen. So let's go back to the starting page. So at the start page, what you'll do, we have this here. Let me just circle it. We have this here. Press on that.
Schematic editor, yes.
Yeah, yeah.
But, and then it says we should create or open project first.
Oh, okay, okay, I see. That's an issue. Okay, so what you're going to do is, were you able to, I hope you were able to download the zip file. I really hope so. So you can now move to file, okay?
Sorry, can you check the message, the chat? They are having problem with creating the file.
Yeah, I see. Wait, what is this? Okay, let me just view this. It's saying that you need to view the files first. Okay. Okay, I see. So, okay, I think we'll just have to have the same screen as mine. That's not an issue. So what you're going to do, come to the file section here. Okay. I hope you are at that point. And then go to open project. Not new project, open project. Okay. And then in the zip file I sent you, open the zip file. Okay. And then go to okay, I can hello. Okay, let me do this. Let me share my whole screen. Let me just share the whole screen. Okay. Let me first resend the zip file and then
never mind. Someone sends it in the chat.
I hope those of you who are in the group are able to see the source file if you hadn't seen it before. So that is where it is. Now let me just yeah, I see somebody sent it. Okay, so what I'll do, let me just share the whole screen. Okay, can you see my screen?
It's still on the first page of the.
Okay, great. So are you able to see this?
Yes, the file systems.
Okay, so for me, I have them separated, but move to the folder that has the file that I sent you. The already opened file, it's a zip file. Open it, and then you can now move into that folder.
We select project Pico main.
Exactly, you select that, and then you can move into KiCad projects, and then Pico WH.
No license.
Yes. And then the last option, I hope you can see it, Pico WH, the last option.
Yes.
And then you can press open. So you can see this is what the files appear. I don't know if on your end it's appearing.
Yeah, it appeared on mine.
Ah, perfect. How about the rest? Abdullah. I see many of the guys here saying it's okay. If you're stuck, you can just say where you are stuck so that you can help. Okay, I see feedback from the chat box. But then this is good. Yeah, this is good. Okay, I see everything is fine. Yeah, so I think we can move forward. What's the time? Because okay, I see it's okay. That's okay. So let's continue. I hope you are at the same point that I am in, or I am at. Now we can now go back to the thing I was telling you to do. Press on this. And it should open something like this. If you're at this point, you can just say something on the chat box if you're able to see such a screen.
There are three options: copy default global symbol library table, copy custom global symbol library table, and create an empty global symbol library table.
Okay. Let me. I think because it's the first time that some of you are doing.
Yeah, that message here.
Create copy. Select copy default recommended.
Okay.
Yeah. I hope you're able to see this screen. Ah, perfect. I see Adam. Yeah, that's good. That's good. Abdul Bassett. That's okay. That's good. Yeah, this is good. Yeah, so I hope everything is okay. Let me continue now from this point. So a number of things. Let's even not go into the schematic first. If we look at the navigation bar, we can see file here. We are seeing, let me now move into just this schematic. So we are seeing file here. You're seeing save, import. These are not going to be much of need. Okay, let me even not go into the navigation bar because there's not much you need to know from this point. Much is on the schematic on itself, on its own. So you don't need to know a lot about that. Okay, so okay, don't know how can I. Yeah, so here we can see a number of things. We can see majority of the things at this point. Here is where majority of the things are, but you're going to go step by step on that. So that's not an issue. So let's start. So as you can see, I'm pointing at something here. I hope you can see the red cursor. I am pointing at something here. So if I want to take a closer look on or at it, I will use the scroll, what is it? The wheel on the mouse to scroll to it, either forward or back.
To zoom, yeah?
Yeah, to zoom. I can be able to zoom onto something. As long as I have the cursor on it, I can zoom into it. For example, this resistor, you can be able to zoom into it. Yeah, USB Type-C connector. I didn't want to mention it because maybe it's not visible well, but anyway, it's okay. I see some of you understand these things. So yeah, so I hope you are able to just zoom as I am. Yeah, so let me continue. So let's start. We are seeing a USB Type-C here. This is, we are selecting it there. Now we can see a resistor. This is R15. A resistor usually denoted by R in KiCad. So this is R15. And what is the value of this resistor? It's written 5K1. What does it mean? It means that the capacity, not capacity, but the value of this resistor is 5.1K ohm resistor. Okay, 5.1K ohm resistor. Okay, I hope you have been able to note that. Let's go into this, for example. This is R10. You can see where it is here. If we go into R10 here, it's called R10, and the names are different. The numbering is different so that you can be able to identify one resistor from the other. And then you can see this one is written 10K. What does it mean? It means that this is a what? 10 kilo ohm?
10 kilo ohm, yes.
Exactly. Now, let us continue to narrow into these resistors. I want to find one that does not have a K. Where can I find one? Yeah, as you can see, for example, this case, we are seeing R3, meaning this is its own unique number. And then we are seeing 470R. So when we see K on the notation, like for example, at the USB-C connector here, we are seeing 5.1K ohm resistor. But in this case, we are seeing 470R. What does it mean? It means that this is a 470 ohm resistor. Does not have a K, does not have a kilo ohm. This is just a 470 ohm resistor. Okay. The notation is people usually have different notations. Okay. Somebody might decide, okay, for 70 ohm resistor, I could just write 470. Depends on how you work. Also, for example, in the 5, maybe they could just write 5.1K. So Yeah, so that is it. So that is about the resistors. Nothing much to see there, just to know that the value is in here. The notation is given, okay? Now, the question is, if we want to select a value for this resistor, what do we need to do? So here, how was I able to select 5K1? How was I able to select 5K1? So what you do is press on that, you select it. You see, I've not selected it. If I select it, it becomes blue, something like blue. The highlight is blue. So you can see I've selected it and the highlight looks blue. And then I press V, okay? And you can see here that I've written 5K1. Let's say I wanted to have a 10K. I'll just write 10K and then press OK. And it changes to the value that I selected. Okay, so I just go back, press V, and then write 5K1. And I go back to what it was.
Okay. Or we can just double click the left button.
Let me see. Yeah. And you can now be able to change. Yeah. That's also, but the other one is a bit easier. This one has a lot of things on the same page. So
yes, true.
Yeah, so that's what you need to do. And then yeah, so I'm done with the resistors, by the way. Let me just go into how do you select these components? You see, so we need to look at how are we able to select the components. So just a moment for these two. Okay, see, there's some comments. Okay, Randa, I see you pressed V and it did not work. Or what? Okay. Okay, you can try double clicking the. Okay, see Abdul Bassett is starting to ask now about the logic of the the design, which is okay. That's no problem. But okay, Abdul Bassett. So this is a schematic I just downloaded off the internet, and usually I usually see most of the time when designing my own PCBs, I usually use a USB micro B connector. I don't like using USB Type-C, but I usually see 5.1K resistors on that C and C2 pin. Articles about it, and it's for termination, a termination resistor. That is what I have talked about. I not talked about, but have seen. But I'll do a bit of research. That is this. I don't really work with USB Type-C because working with USB micro B is easier. And let me show you an example. Let me just give you an example. Okay, I don't know why is this. Okay, let me just show you the USB Type B resistor here. And you can see where they have many USB types, but I usually go for this USB B micro. And this is, you can see it's very easy because let me just draw. I can be able to connect this to 5 volts. Where is it? I can be able to connect this. Okay, drawing here is very difficult. Don't know. It's so difficult. Writing 5 is so difficult. but the V bus can be connected directly to, yeah, I see somebody's writing 5 volts, perfect. Then I can now connect ground here, just to ground here, okay. Shield does not usually having a metallic shield that is also connected to ground. You can now connect them. ID is also not usually connected. So we usually connect most of the times V bus, D plus, D minus, and ground, okay? These are the ones that you usually connect most of the times. So you find that it's usually easy for me to use USB B micro, and I'll show you some of my projects. All of them, I use B micro because you can see this. And then I want also now for you to compare with what? With, let me just go back to selection. With this. And you can see this has so many pins. And it's all going towards the same objective, which is connecting USB. So, but I'll give you more clear answers on this. I don't, I'll be honest, I don't work with these USB Type-C, so it's quite difficult for me to know. But what articles I've read is this is a termination resistor. Okay. Okay, great. Let me continue. So we are saying R2 here. Okay, we are done with the resistors. I will not go into resistors again. Let us move into capacitors. So we want to see, this is a capacitor, this is a capacitor, this is also a capacitor, okay? And now, okay, I'll not go into reasons why capacitors, okay, I'll go into it. So you can see here, we are seeing, to those who have interacted with capacitors before, you know that we usually use microfarads, okay? Or we usually use units of farads. So meaning that when we are now putting values here, for example, you can see here, we are writing 47U. What does it mean? 47 micro. But because we cannot get the mu, I don't know, it's usually Greek or something, we cannot get it in KiCad. We just usually write U to represent mu. So 47U means 47UF, okay? So usually, so even to change the value for this, you just press V. And you come and write 40. This is 47U, and you can write F. I usually want to use F, not writing just U. So somebody can see this is 47 microfarads, okay? This one, we can also do the same thing. We can go there and write capital. This should be capital. So that is 47 microfarads. So that's how you, any component you see, you can get the value through using V, okay? Then we can see other capacitors here. We are seeing 100N. Who could tell me what that means?
Nanofarads.
Exactly, nanofarads.
Yes.
So that's a 100 nanofarad capacitor. Here we are having 2.2 microfarad capacitor. Where else? What about
Pico.
P? Exactly.
Pico.
15 picofarad capacitor. And these ones, and also for people to know, we are not just picking these values randomly. These values are not random. We are supposed to know where they're coming from, but that is not something I'll be able to cover in this talk, unfortunately. But I hope you understand that you need to know where these things are coming from. Next, here we are seeing inductor, okay? And inductors are typically usually very few in our schematic, depending on the, but mostly the ones that I've worked with, inductors are very few. So this is an inductor here. And somebody might ask, and I like how Abdul Bassett was asking questions. And that is a mentality that we need to be going with in this, because we need to ask, why are we having this resistor, this inductor here? Or why do we have this resistor here? Why is it specifically 100 kilo ohm resistor because the moment you know these things is the moment now you're able to create something on your own. And also, and this is where now there's usually a variation between what we learn in class and what we see in the industry. Since, okay, I don't know, but the Kenyan what model is, we have learned about voltage regulators from a long time before. Not voltage regulators, but voltage dividers, meaning that you're having two resistors arranged and you are getting the voltage at the center. And that is a voltage divider. You're able to divide the voltage into two. And usually we learn this in class. But you're not usually taught where they apply. You're not told, okay, this is where you're going to use it. But you see here, we are using that concept in this board. And what we are doing here is we are having a voltage divider here. And it is splitting the voltage in a ratio of what? 5.6 to what? To 1. Okay. And now we need to be asking ourselves a question. How do we have 560 here? And why do we have 100? And that is now where you start learning. That is now where you can be able to understand. And the question is, why not have maybe 460? Why is it specifically 560? Okay, but I'm not going into that today because of time. Time is not on our side. Anyways, okay. So that is an inductor here. I also see somebody on the chat is asking, what do LX1 and LX2 mean? This means that usually every component, okay, usually has a way that they call their pins, the denotation. And LX1 is how the company that created this chip calls pin 8. They call pin 8 LX1, they call pin 6 LX2, okay? And when you read the data sheet of this specific chip, they'll tell you that you're supposed to connect LX1 to a resistor, or to an inductor, to an inductor of a specific value, okay? And we are going to go into data sheets. I don't know if we get time today, fine. If not, we are going to have another meeting, hopefully. But that is how, yeah, it's not anything about that is the pin name, okay? But if you read the data sheet, they'll say pin 8 and 9 and 6 and 7 needs to be connected to an inductor of value 47 microhenries or something, okay? So that is something that these pins, their definition could be given through what? The data sheet. So I see somebody also asking, could you start by making a very simple PCB? That's okay. I think that is what we're going to go next into, because I know seeing this is very complicated.
Complex.
You
Yes.
see people seeing very complicated stuff here. Hello, can you hear me? Hello?
Yes, it was lagging a bit. We can hear you now.
Oh, sorry. Okay. So you can see here, I see Abdul Baset is asking questions about decoupling capacitors. And you also have someone else also saying, okay, could you start by making a very simple PCB? And you can see we are having two people with different levels of understanding, which is okay. And I think what you're going to do today, we're going to focus on the beginner side. If we get time another day, we are going to go into now intermediate stuff and finally expert stuff. So today, let's focus on intermediate. So don't be afraid of this. The reason why I'm showing this is just to show you that resistors, capacitors exist on a circuit. The next thing we're going to do, we're going now to create a small schematic. So that is not an issue, okay? So we have seen resistors, we have seen capacitors, we have seen inductors, okay? I think those are the major things I wanted to show you in this schematic. Now what we're going to do, let us move into now creating our own PCB, okay? So
Yes.
let us move into, I'll explain this in a certain session. Don't be worried about it. I know there's many things here. I don't know, somebody might ask, what are these for? Or what are these? They're going to explain them. So that's not an issue. Let us first create something, okay? Because it's supposed to be practical. So let us first, let me go into sharing the entire screen. The first PCB is going to be very basic. I just want to show you the stuff that exists on KiCad. I don't want to go into. So let's go into file. Okay, I hope you're there. In the main page, we go into file. And then we go into now new project. Last time we picked open project. This time, let us select new project. Okay. And we call this new project first project. So I usually save my, so let us have them there. Once you save it, you should be able to see a screen like this. I hope you are here.
Yes.
Okay, let me wait for about 10, 20 seconds and then continue. Okay, great. So we can now go again into schematic. Press same method we used last time. Just press what schematic. I hope you're able to see the screen.
Yeah, it's we can see.
Okay. Yeah. So I think we are okay till this point. Now I will be using a lot of circles. I hope you can be able to see this icon here. So what you're going to do, click on that icon. And mine has just loaded, but yours is going to load for a bit. Okay, it's going to take a while, about a minute or two. And I see in a thumbs up if somebody can see such a screen. If your screen looks like this, okay, I see Zaran. Okay, Randa is here, it's loading. Yeah, it loads fast. ASMDH, don't know who MDH in full is. Okay, seems like he's worked. Or, okay, I don't know, it's a lady or a gentleman, anyway. Okay. Yeah, it's going to catch up. Randa, is it okay now? Still loading. Okay. Yeah, actually, for the first time, it actually loads. It really loads. Okay, great. I was waiting for Randa to. Okay, now what you're going to do, let us pick. We basically want to do a very simple thing, okay? We want to light an LED. Very simple, okay? So what we are going to do, we are going to just press R and it's going to bring a resistor. Just press R, okay? And when you press R, you're going to see something like this. This is what shows you it's a resistor, this here, okay? So once you see this, press OK. And you can be able to see something like this. You can zoom in and zoom out. You can click to place it somewhere. It moves around, and then when you click on it, on a certain position, it basically puts it at that point. Don't know if you've been successful till this point.
Yes.
Okay, that's great. So yeah, so what we want to do is to have maybe 3 LEDs being lit at the same time. Maybe, okay, but this will make it a bit complex. I don't know. Let me see. That's okay. That's still okay. So what you're going to do, let's have 3 LEDs. So instead of again pressing this point and going to, we can duplicate this by using a shortcut, Ctrl-D. You press first, you see, I've not pressed anything. Press on the resistor and then press Ctrl-D. And then you can create the second one. And then Control-D.
Control B or D?
D for dog. Let me just write D on the chat box.
Oh, D, okay.
I hope you have been able to get to this point.
Yes.
Okay, that's good feedback. Okay, I think we can continue. Now we need LEDs. Okay, I like that. Now we go back to this point here. Let me just we go back to this point here. Where is it? This point here. And then we press it again. Okay, and it brings this dialog box. And then we again write LED. Right? And then after this, you'll see something like this icon, the very first one. Press OK. And then you can see that in this case, we can be able to move it around until I click on a place. But you see, I want all these things to face downwards. So this is facing horizontal, but I want it to be vertical. So you can just press R and it will rotate. If you press R, it rotates. So press R until it gets to a point where this is how it looks like. Have you been able to get to this point? Okay, I hear somebody is okay. Okay, yeah, I see someone else. Okay. Perfect. I see a number of people. Okay. So now again, what do? We duplicate the LED 2 times. Control D. We press it. Control D. Okay. Or to move them, okay. Once you have placed them, just click on that and then hold down the left button. You can see. You first click on it. First click on it. This is not selected. Selected, and then you hold down the right button, mouse button. It was Randa. Randa, have you been able to do it? Perfect. So from this point now, we know that any kind of LEDs, they usually have a specific limit of current. And we are using these resistors to limit the current that is going to pass through. Or, okay, to some extent, maybe, let's say that we are feeding it maybe 3 volts, maybe, don't know, 3.3 volts. So we have to limit the current through these resistors because it's the current that determines how bright the LEDs light, but they again have a limit. But typically, if you've done projects on the breadboard, you find that when we are pairing an LED with a resistor, we usually pair it with something like to 20 ohms, 680 ohms to around 1 kilo ohm. Okay, so what you're going to do, we are going to press the resistor, the first resistor, and then we press V. Okay, and now it's just written R. So we just press, let's have a 1 kilo ohm resistor. We write 1K and then press OK. And you can see now we have given it a value. And then you do the same for the next one. Press V, write 1K. Okay. Another one, press V, 1K. Okay. I hope you have been able to get to this point.
Yes.
Okay. Perfect. And then lastly, we now want to add power. And let's say you're going to feed this circuit 3.3 volts. Okay. So we are going to write 3. Oh, sorry. I didn't show you where to select. Let me show you where to select. So now we go for the icon that is beneath the one that we were selecting. This one here, that looks like the earth symbol. Click on that and just write 3 only. And we first see 1V35, note that. The second one is plus 3.3 volts. Okay. Press OK. And press it, put it there. I hope everything is okay.
Is this like the current we are going to use?
The voltage source.
The voltage.
Yeah, 3.3 volts as the input. Okay, I see Hashem is lost. So you see the place I've circled here. Click on that. Okay, and it will bring this dialog box here. And then press 3. And then select the second option, which is plus 3.3 volts, and press OK. Perfect. So we have selected, okay, this is, so we have the 3.3. I hope everyone has something like that looks like this. Lastly, we know that when current is moving, it moves from high voltage to low voltage. Okay. So we again know that earth or ground is at 0 volts, right? So if we are moving from 3.3, meaning it should end at 0 volts. So we again press the same place that we pressed there and write GND. Just write GND, and it will give you this kind of diagram here. Not diagram, but symbol. And then you press OK. And then you place it at the bottom. And you should have something like this, something similar to this. Okay, this meeting was supposed to end at 11. We're just going to go to around 11:20 because this is taking too much time than I thought. Okay, I think we'll have to move a bit fast. Okay, till that point, is everyone okay?
Yes, yes.
Okay. Next, we now come to select, and now beneath this power symbol, we select wire, or even you don't even have to select wire. The moment you move the cursor to any point, you see, for example, this. Let me just draw. You see, for example, where is it? This point here. If you move the cursor above that point, you see it becomes something different. It becomes like something green appears. I don't know if all of you can see that. If you move it above, even in the resistors, we see something green.
It's highlighted, yeah.
Yes, you can see it.
Yes, yeah.
Ah, perfect. So you now click left click on that, and then you can start moving. This is now the wire. This is the wire. Now you can maybe move downwards, and then you can click. I know I've moved a bit fast there, but I hope you can be able to replicate something like this. You basically just have you been able to do this?
Yes. So either we use the wire option or we just drag the mouse.
Exactly. It depends, because there's some cases where you might, but this is the best. It's easy. It's an easy option. Just hover the mouse above
Yes.
it's easier. Okay.
And
Then
we button Control plus Z.
oh, okay. Control Z.
Yes.
Oh, okay. Then again, we can now finish up on this. We can now this. Okay, to those who want to redo and undo, if the buttons, the shortcuts are not working, you can move to edit here, and you can see here we have the redo button and undo. So you can just go to the navigation bar, go to edit, and you can select either the two options, either to redo or undo. So yeah. Have you been able to get to this point?
Yes.
Okay. Now, from this point, now we can move into, now here, we already have the logic finished. The logic is already done here. We already have the power supply. Let me just draw this. We already have the power supply here. We have the resistor to limit current here. We have the LED light, and then we have the ground at 0 volts, 0 potential. Okay, so you have basically done, or we have been able to do all these things here. So I see Mohammed saying the period is over. Yeah, the time is actually over, but I think I'll end it at 11:20, because it's supposed to be practical. So I think I'll just end it at 11:20, and then we also need to have the end will be around 11:30, because we also have a link for the some question. Yeah. So
Okay.
yeah. So let me just move fast. Next thing after this, I'll not explain a lot of the things, but okay. So next thing is move to this icon here. Okay, I even undo. Move to this icon here. Okay, and then select it. This should also load. You can see mine is loading, but it should not take a lot of time. Okay, as it loads, I don't know, mine is taking a bit of time.
Try closing it and reopen.
Yeah. Oh, I see already Adam.
Yes.
Okay, we can just continue. So I think at this point, because you also have again to go into the PCB and then you also have to root, it might take a while, but I think we're going to end it here at the assigning of footprints. Note that we at least we have covered the schematic section, and then we can have another session to cover the PCB. And I think we will now go into details on it. So let me see. Yeah, so mine is now open. Okay, it took a while there. So number one, we want to assign footprints here. Okay, we want to assign, there's somebody who showed a symbol there. That is the symbol. So come and press the first one. It will become blue. And then now go to the side, the sidebar, the left side, and then scroll and look for LED THT. Okay. LED, scroll on the side, on the left side. Go to the L section and look for LED THT. Have you been able to see that?
Sorry, I have a question.
Yeah, Adam, yes, there's going to be a quiz. Yes.
The footprints, what are they made for? What are we need for them for?
Okay, so you find that there's many types of LEDs. Yes, we might show that an LED has 2 terminals, but there's so many types. There's a clear LED. There's an LED that is so small. You're able to select between what LED are you choosing. You want to be very specific because you cannot tell a manufacturer that I just need an LED. You need to also specify what type. Okay.
Oh, it's like a model, the model of
Exactly.
okay.
And I wish we had time to go into the PCB so that you could see it. You can be able to see it.
Okay.
So let's just move fast. So you go to the LED THT here, and then when you look at the side here, you will see number 16, okay, which is written LED, and at the end is written clear, okay. Double click on that, and it will appear. And you select D1, double click on that. Select D2, double click. D3, double click. I hope everything is good until that point. Okay, I think those who will be able to follow will just follow because of time. And then we now move to R1, select R1, and we go in, we now look at the right side, not right, but left, the place we were looking for at the start. Look for resistor THT, okay? And select number 16 again. So for R1, select number 16, R2, number 16. You double click, what is it? The left button, yeah, the mouse button, left mouse button. And once you're done, you press apply and save schematic, okay? And then you press okay. And you have been able to choose the resistor. You have chosen a specific, because resistors are many. There's many types. So you have selected a specific resistor, a specific, resistor and LED. Now we move into, okay, here we are not going to route anything. I just want to show you how, what we have done looks like. So there's a green button there, a green kind of symbol or something. You press that. Okay. And it opens this page here. I hope those who are following are able to follow till this point. And then there's this one here. It looks green, and at some point it looks a bit of half green and something. It has green. Press that. And at the bottom, let me just show it. At the bottom here, select update PCB.
I think the new screen is not appearing to us.
Oh, okay. Yeah, I didn't share the whole screen. Okay.
That's okay.
Okay. Let me repeat. So we have this one here. So click on that. Okay. And then we have update PCB here. Click on update PCB. Okay. And then press close. And then again, this also moves. So you're supposed to click somewhere so that it has a place to stay. And this is what we have created in the schematic. Okay. We are not going to route anything. We're not going to connect them. We have just placed them. Okay. We just place them somewhere on the, as long as it's on the screen somewhere. So I hope those who have been able to get this point successfully, congrats to you. Lastly, this is the last thing we're going to do. This logo beside this one, let me show you this logo.
Icon.
There's this logo here, this black one here. In order for you to see the PCB that we created, also press on that logo. So this is our PCB that we created. And we chose this specific PCB. That is what we were doing at the footprint. We chose this specific LED. We chose this specific resistor. Yeah, we actually done. This is the last thing that I have done. So I wanted for you to see so that you can be able to see the what is going on. So these are the resistors. These are the LEDs we chose. So I think till that point, this is what I wanted to show you guys. And I've been able to do it. We have been able to, those who have been able to follow, we have been able to do a project from start to be able, so that you can be able to see the PCB. So I think till that point, we are okay. And now we can go back to the presentation. Yeah, we can go back to the presentation. And perfect. Yeah, so we are seeing okay. Yeah. So KiCad demo, we did the KiCad demo, we did a project demo. Conclusion, this we have talked about. How to keep learning. This is the last step, the last thing in my presentation. Practice. And we started here writing, start with a simple circuit as we did. That is the best place to start. You start at that point. That is where you start. KiCad resources. And out of all these that I've written here, the best thing I can tell you to do is to go to YouTube. YouTube is the best place to learn. Let me write this channel so that you can go and look for it. Go and look for that channel. That is the best place you can learn these things. We have the Fields Lab is a really good place to learn. And with that, final inspirational message. You have the knowledge to bring electronic ideas to life. Go create something amazing. So you don't necessarily have everything, but you have something to start. I'll send you the URL and the group, no problem. So yeah, and finally, thank you. So that is my email. That there's my email, and that there is my phone number. So if you intend to reach me out or something similar, just reach out. And
Can I ask you a question?
Yeah.
It's actually between the workshop itself, but I want to ask if you do this for just a hobby or you as a business or what?
Okay. So at the moment, I do it as business. I have a channel. Okay, I do it in two ways. I have some local guys who send me ideas and I print the PCBs, and then they basically pay for my services. And we also have Fiverr, not Fiverr, but yeah, Fiverr. Also there I have a portfolio that I use it to show my projects, and people send me work. So yeah, but it's something that I've been doing for maybe around 4 months now. That is the Fiverr one. For the local company projects, I've been doing them for about 8 months. So I'm quite new to Fiverr. It's a bit of a learning curve, but I think I'll be able to. You see, Fiverr is not people make money from Fiverr, but it's not the fact that you know PCB design does not mean that you will be chosen. There's also the aspect of marketing. You have to use keywords in order to get clients. So you might be very knowledgeable in PCB design, but you may not be successful in Fiverr. So yeah. So lastly, let me send you the link. I don't know. The link should have, yeah, somebody is sending it. Okay. So as we wait for the link to be sent, any final questions? Yeah, we have the link there.
Yeah, the quiz have been received on the chat. Everyone, you can go and start your exam. As we said, as you score 60% or higher, you will be able to receive the certificate. Mr. Ian, you are sharing the screen for the quiz, so please don't solve it in front of the attendees. They need to try for themselves.
Okay. Let me just stop sharing the screen.
Thank you for
Yeah, please.
everybody. And bye.
For Arabic speakers, السلام عليكم. الكويز موجود حاليا على الشات، تقدروا تشوفوه. اللينك موجود. حلوا الكويز. أي حدا بجيب 60% فما فوق من الدرجات تكون الشهادة موجودة له إن شاء الله. الشهادة بنبعث لكم إياها بحدود بكرة على نفس الجروب. رجاء خليكم في الجروب لحد ما توصلكم الشهادات. بعد ما تستلموا الشهاده يعني احنا راح نطلع اصلا الجروب من الكوميونتي، وانتم تقدروا تطلعوا من الجروب او تضلكم فيه يعني براحتكم. وشكرا جزيلا لحضوركم معنا اليوم. بتمنى كانت الورشه مرتبه. اي حدا عنده اسئله يتفضل، وهحكيها بالانجليزي برضه. Anyone, if you guys have any sort of questions regarding the session, please share them with us during these minutes. And thank you very much for Mr. Ian. He has done a great job at this workshop. He explained all the basics, went from the start. It was wonderful. I watched the whole thing, and I hope everyone has learned from this workshop. And we are waiting for you to solve the exam. And if you have any questions, ask us. Don't hesitate. Please open the mics whenever you feel for it.
Thank you. It was a wonderful meeting, but there is a question on the chat. It's asking how can we improve even more.
Mr. Ian,
Okay.
are you with us? Yeah, can you answer
Yeah.
the question?
Yeah, I have sent you link. I've sent a link for our YouTube channel. That's the first thing. That is the answer to that question. You can be able to go there. But another thing that I will say is, if I look at the journey of how I got into PCB design, what I was doing is I was going to a YouTube video, and the YouTube video is maybe 4 hours long. And you find that you are basically pausing the video and copying what they're doing. You may not understand what is going on, okay? But in these videos, slowly they keep on explaining. They say, okay, this resistor, these values for this, and you learn slowly as you go. So that is why I usually love YouTube, because you can be able to have a video, and this video is maybe 4 hours long. So you can go through that video and they will be explaining as they go. So you learn slowly. And the more you do these projects, the more you understand KiCad, the more you understand PCB design. So that's what I can say. That's the best thing I can say. Go to YouTube, learn. Even once you get better, try and go to what is this? Go and download schematics and try and make a PCB. Okay, so those are the ways that you can do this. Yeah. Okay, let me just send you the link.
Sorry, I have a question.
Okay.
What is the silk screen layer?
Okay. Silk screen is whereby you have a logo, okay, and this logo, you want it to be seen on the board.
Labels.
Labels, and also a logo. Maybe you have a company and the company wants maybe the logo to be displayed on the board. So that is what you use. Silk screen. It's called silk screen.
Yes. Thanks for the explanation.
Yeah.
Sorry, I have another question.
Okay.
So when we save our PCB document, is it an image file or what is
Okay,
the
I see.
type of the file?
So there's something called GABA file. Okay. So you don't send the image because, okay, there's sometimes you have very I would say, what the PCB should not be shared by to anybody. Maybe it's something new. So usually you share something called a GABA file that tells them where the components are going to be and everything, but it does not give them the schematic or the PCB design schematic. So you're just given, this is how it's basically giving you kind of positions where to etch and to place the footprints, but you're not being given the schematic. So you're sending a kind of a file that is quite difficult to reverse engineer. It's possible, but quite difficult.
Okay, its name is Gerber file.
Exactly. Yeah.
Thank you. Thank you.
Yeah.
How much time we have left?
I think I don't know, because you're supposed to finish the document. I don't know after that what happens. Yeah.